Alright, so straight on to question 2 here. This looks to be about the photoelectric effect. So ultraviolet radiation falls on a tin plate held by an insulating support. The plate acquires a charge. Explain in terms of electrons and photons why this happens and whether the charge is positive or negative. So what's going on here? Here's my plate. Some photons are incoming. They are taking negative electrons out. Therefore, what is left is positive. So I just need to put that in words for 3 marks here. Explain in terms of electrons and photons. So we need to use those words. Whether the charge is positive or negative needs to be included as well for my 3rd mark. Okay. I suppose I should say incident photons. So let's say that. Incident photons. Give electrons energy to leave the tin surface. Since electrons are negative, tin is left positively charged. And hopefully that is all I need to say, really. One would hope. So the work function here, phi 7.1 times 10 to the minus 19 joules. What is meant by the work function? So it's the energy required to remove an electron from the surface. Energy required to remove an electron from the metal. I could, I guess, put minimum. Calculate the minimum frequency of ultraviolet radiation needed for photoelectric emission from tin. So that would happen when the photon energy HF is equal to phi, the work function. So therefore the frequency would be phi over h, Planck's constant. So that gives me 7.1 times 10 to the minus 19 over Planck's constant, which is 3.34. Oh no, wait, it isn't, is it? It's 6.63. 6.63 times 10 to the minus 34. Always look up your constants in the formula book. Never rely on memory, especially if your memory is as ropey as mine. So that looks like a job for the calculator. Let me plug that in. 7.1 times 10 to the minus 19 divided by 6.63 times 10 to the minus 34. And I've got 1.07 times 10 to the 15. So 1.1 times 10 to the 15 hertz. Calculate the frequency of ultraviolet radiation needed for the emitted electrons to have a maximum kinetic energy of 1.5 times 10 to the 19. So the formula we're looking for here is this one, HF minus phi, because the work function is required to escape the metal, so the leftover energy, which will be in the form of kinetic, is simply the energy of the photon that's been absorbed minus that work function. So, and that is a maximum kinetic energy because, of course, the electron could lose some additional energy on its way out of the metal, i.e. phi is the minimum energy required, so slightly more than that could be required. So I don't want to do equals there, do I? I'm trying to find a frequency. So frequency equals this kinetic energy that we want plus phi divided by h. So again, I'm going to plug in the numbers. I've got 1.5 plus 7.1. Both of those are times 10 to the minus 14 divided by Planck's constant, 6.63 times 10 to the minus 34. And again, that's very much a job for the calculator. So 8.6 times 10 to the minus 19 divided by 6.63 times 10 to the minus 34. This time I've got 1.3 times 10 to the 15 to 2 sig figs hertz. Okay. So this is a pretty standard setup, frequently used for measuring or trying to get a number for Planck's constant. So in this setup, assume that all of the electrons emitted from the tin surface are collected by the electrode and returned via the microammeter and the power supply. So I've got ultraviolet radiation of frequency 1.3 times 10 to the 15 coming in. Yeah, this is an interesting setup. I notice that it's this is not a stopping potential. Look at the way around the plus and minus are. So this potential difference that's being offered up here is giving these electrons additional energy to cross this gap. But perhaps that doesn't look like that's going to come up in the question. So we've got a reading from the microammeter, 0.64 times 10 to the minus 6 coulombs per second, to show that 4 times 10 to the 12 electrons are emitted per second. So all we have to do here is turn that charge into the number of electrons. So Q over E will give me the number of electrons. So that is equal to, in 1 second, 0.64 times 10 to the minus 6 divided by the charge on 1 electron, 1.6 times 10 to the minus 19. I don't need to worry about the minus sign here. This is a straight count. And I've got, that is exactly 4 times 10 to the 12 as required. Arguably I should put in the 4.0. Only 1 in 1,200 of the incident photons causes emission. By considering the energy of an individual photon, calculate the ultraviolet energy falling on the tin surface. So I am given the frequency of the radiation. It is 1.3 times 10 to the 15 hertz. So energy of 1 photon equals HF, so 6.63 times 10 to the minus 34 multiplied by 1.3 times 10 to the 15. And actually my previous answer, if I look at the calculation I did here, I can see that when I multiply those two together, I've got 8.6 times 10 to the minus 19. And that is a number of joules. The number of photons per second then is equal to 1,200 multiplied by my previous answer, multiplied by that number of electrons. Since only 1 in 1,200 of them are actually emitting electrons. So what is that? That is a large-ish number, isn't it? 4.8 times 10 to the 15. So energy per second equals those two multiplied together. The number of photons per second multiplied by the energy of 1 photon. So I'm going to put that one in the calculator, I think, rather than trust my fairly shoddy mental arithmetic. And that gives me 4.1 times 10 to the minus 3 joules per second or watts. And that should be that. And that is the end of question 2.